Are you tired of tackling your scientific problems using boring old Euclidean geometry? Looking for a fresh approach to bring joy back into your academic life? My friend, let me introduce you to the world of numerical integration. But with geometry, I can figure out the area of a rectangle. With integration, you can figure out the area under any curve. But with geometry, I can figure out the circumference of a circle. With integration, you can figure out the length of any continuous arc. But with geometry, I can figure out the volume and the surface area of a cylinder, and even a cone. With integration, you can figure out the volume and surface area of any three-dimensional solid of revolution. But don't I need to follow a bunch of esoteric rules in order to solve problems using integration? With numerical integration, you don't need to know any of that, so you can start solving problems right away.
Wow!
What is this magical integration that you speak of? Well, let's find out. Welcome to QuadGK.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. Knowledge of calculus is not required for this tutorial, but this tutorial is a continuation of the previous tutorial, episode 806, which introduces the subject of calculus using Julia. You should watch that video before watching this video. I'm also assuming that you know how to use Julia and that you know how to use Pluto Notebooks. By the end of this tutorial, you'll know what numerical integration is and how to perform it in Julia using the QuadGK.jl package. With that said, let's get started. In the last tutorial, we learned that calculus is the study of continuous change, and that there are two main branches of modern calculus, known as differential calculus and integral calculus. Differential calculus is about instantaneous rates of change and the slopes of curves, while integral calculus is about accumulation of quantities and areas under or between curves. Using a computer for differential calculus is known as automatic differentiation, while using a computer for integral calculus is known as numerical integration. So what exactly is numerical integration? According to Wikipedia, numerical integration comprises a broad family of algorithms for calculating the numerical value of a definite integral. Numerical integration is sometimes referred to as numerical quadrature. This is what the notation for a definite integral looks like. This is read, the integral from a to b of f of x dx. The elongated s is the integral symbol, which was first introduced by Leibniz to stand for summa, which is Latin for sum or total. An integral is calculated by summing up infinitesimal slices of a function. The variables a and b represent the lower limit and the upper limit, respectively, of the interval a comma b of the real variable x. This interval is called the limit of integration. By specifying limits, the integral is called a definite integral. That dx symbol at the end is called the differential of the variable x, which indicates that the variable of integration is x. The process of calculating the integral is called integration. Using a computer for integration is known as numerical integration. There are several different algorithms that are used for numerical integration. One of those algorithms is called the Gauss-Kronrad quadrature formula, named after Carl Friedrich Gauss and Alexander Kronrad. Alexander Kronrad was a Soviet mathematician and scientist, and he invented the Gauss-Kronrad quadrature formula in 1964. The QuadGK.jl package is the Julia implementation of his formula. QuadGK.jl used to be part of Julia Base, but it's a separate package now. I'm not sure who the original author is, so I apologize for not giving proper credit to the creator. The best way to get to know the QuadGK.jl package is to use it. So let's take a look at some examples. Let's fire up Pluto and create a new notebook. Let's start by adding the QuadGK package, along with ForwardDiff, plots, and Pluto UI. Let's define a generic function to use as an example. For this demonstration, I'm using the square root of x, but you can replace this function with any continuous function. Now that we have our function, let's set up a couple of sliders that we can use for the limits of integration. By convention, a is used for the lower limit, and b is used for the upper limit. In practice, the value of a should be lower than the value of b. But since our sliders have the same range, let's set up the range of the x values in a way that will allow for any value of a and b. Now, let's calculate f of a and f of b. I'm rounding these values, but that's optional. As a refresher from the last tutorial, let's find the derivative of f of x at a and at b by using the ForwardDiff.jl package. Again, the rounding is optional. Okay, we now have everything that we need in order to evaluate integrals. Let's start by finding the area under a curve. By definition, the integral of the function f of x is the area between the curve and the x-axis. The main function in the QuadGK.jl package is appropriately named QuadGK. The QuadGK function takes 3 arguments. The first argument is the function to be evaluated. The second argument is the lower limit. And the third argument is the upper limit. The QuadGK function returns a tuple. The first element is the solution, and the second element is the error. As long as the error is some number close to 0, you don't need to worry about it. What we're really interested in is the solution. Again, to keep things simple, I'm going to round the solution. So this number means that the area under the curve defined by the function square root of x from the interval along the x-axis from 0 to 4 is around 5.33 square units. This solution is a little abstract, so let's generate a plot to see what's going on. Let's start by adding some markdown text so we can see some numbers. We need to place the plotting recipes inside of a begin-end block, so the code inside of this cell will be a little long. Before we talk about this plot, let's pull down our sliders and then hide some of these cells. The orange curve is the function f of x, which for this demonstration is defined as the square root of x. The green horizontal line is just the x-axis. The blue shaded region is the integral from a to b of f of x dx. By definition, this result is the area under the curve and above the x-axis. By using numerical integration, we calculated that the area of this blue shaded region is roughly 5.33 square units. As a sanity check, the area of a rectangle having a width of 4 and a height of 1.5 is 6 square units. So that makes sense that the area under the curve is some number lower than 6. Conceptually, what's going on is that you're taking a bunch of vertical slices along the x-axis from A to B. Each sliver has a length of f of x, and each sliver has an infinitesimal width. The sum of all of those infinitesimal areas adds up to the total area under the curve. You can use the sliders to change the values for the lower limit and the upper limit. As you can see, both the shaded region in the plot and the area calculation in the markdown cell update automatically. Pretty cool, right? But wait, there's more. If you rotate this shaded blue region around the x-axis, you'll end up with a three-dimensional object. By using numerical integration, you can calculate the volume of that three-dimensional shape. Let's learn how to do that next. A solid three-dimensional figure, formed by rotating a two-dimensional figure around an axis, is called a solid of revolution. Conceptually, rotating a curve drawn on the xy plane around the x-axis is like drawing a bunch of circles around the x-axis. But rather than drawing the circles in the xy plane, you need to draw the circles in the yz plane. The radius of each circle is f of x, for every value of x within the interval. We know from geometry that the area of the circle is pi r squared, and that the volume of a cylinder is pi r squared times the height. Now, if you take this concept and squeeze the height down to some infinitesimal unit, then you can estimate the volume of any object that's generated by rotating around an axis simply by adding up the volume of all of those skinny cylinders. I know that it looks funny, but the function to be evaluated here is the same as pi r squared times some infinitesimal unit, where the radius is equal to f of x. You'll be happy to learn that we can use the QuadGK function to calculate this volume. Rather than using f for the function, we can use an anonymous function, which is the translation of this LaTeX equation. Again, this is optional, but I'm going to round this volume to keep things simple. So the QuadGK function has calculated that the volume of this three-dimensional shape is around 25.13 cubic units. As a sanity check, the volume of a cylinder with a radius of 1.5 and a height of 4 is roughly 28.27 cubic units. So that makes sense that the volume of our shape is a little less than the volume of that cylinder. Now, this is a little tricky to visualize. I'm not aware of a rotation plotting function in the plots.jl package, but we can create our own DIY version. Let's start by creating a circle plotting function that will plot a circle in the YZ plane with the center at the x-axis. This function is just using trigonometry to find the coordinates of the circle and returning the x, y, and z coordinates, so we can plot the circle in three-dimensional space. Next, let's create a looping function that will generate 20 circles along the x-axis. Each circle will have a radius equal to f of x for any given x. As a side note, you can use more than 20 circles to generate a smoother 3D surface. But I have some performance issues on my computer if I use more than 20 circles. Finally, we need to generate a 3D plot by including some plotting functions within a begin-end block. Before we talk about this plot, let's pull down the markdown cell and the sliders. Let's add some markdown for the volume. That black line in the middle of the circles is the x-axis. For the volume of this shape, you need to imagine that each circle is a solid disk of infinitesimal thickness, and that there is one of these skinny solid disks for every value of x within the interval. If you add up all of the volumes of all of those skinny disks, you'll end up with the volume of the entire 3D shape. Like in the 2D plot, you can change the lower limit and the upper limit by using the sliders. As you can see, the plot updates automatically, as does the volume calculation in the markdown cell. As you squeeze the circles closer together, you can see that it appears to form a continuous surface. Cool, right? But wait, there's more. Not only can we use integration to calculate the area under a curve and the volume of shapes, we can also use integration to calculate the arc length of a curve. Let's learn how to do that next. If you take 2 points along a curve and draw a straight line connecting them, that line forms the hypotenuse of a right triangle with a base of length x and a height of y. We know from geometry that the length of the hypotenuse of a right triangle is the square root of x squared plus y squared. Now, if you take this concept and squeeze the distance along the x-axis down to some infinitesimal number, then you can estimate the length of that infinitesimal segment of the curve. By adding up all of those infinitesimal segments along the curve within the interval, you can calculate the length of that arc. By convention, the arc length is denoted by the lowercase letter s. I know that this LaTeX looks funny, but it's basically the Pythagorean theorem in a different form. Like our previous 2 examples, we can use the QuadGK function to calculate the arc length. Again, we can use an anonymous function to translate this LaTeX equation. dy dx is the derivative of f of x, so we can use the derivative function from the ForwardDiff.jl package. Again, this is optional, but I'm going to round the arc length to keep things simple. So the QuadGK function has calculated that the arc length of the curve f of x, when x is between 0 and 4, is around 4.65 units. As a sanity check, the hypotenuse of a right triangle with sides of length 4 and 2 is roughly 4.5 units. So that makes sense that the arc length is slightly longer. In order to visualize this, we can reuse our 2D plots. Let's add some markdown text to display the arc length. The arc length is for the segment of the arc between the lower limit and the upper limit. If you move the sliders, the limits will change and the arc length calculation in the markdown cell will update automatically. Nice, right? But wait, there's more! If you rotate this arc around the x-axis, you'll end up with a hollow three-dimensional shell. By using numerical integration, you can calculate the surface area of that three-dimensional shell. Let's learn how to do that next. Conceptually, calculating the surface area of a curve rotated around the x-axis is similar to calculating the volume. But instead of using the area of a circle, we need to use the circumference of a circle. We know from geometry that the circumference of a circle is 2 pi r. As in the volume example, the radius of each circle is f of x for every value of x within the interval. We also know from geometry that the surface area of a hollow open cylinder is the circumference times the height. If you take this concept and squeeze the height down to the infinitesimal arc length, then you can estimate the surface area of any object that's generated by rotating around an axis simply by adding up the surface areas of all of those skinny, hollow open cylinders. By convention, the uppercase letter S is used for the surface area. I know that this LaTeX looks funny, but it's basically the circumference of a circle, which is 2 pi r, times the arc length. R is the same as f of x, and we just covered that equation for the arc length in the last section. Again, we can use the QuadGK function along with an anonymous function to calculate the surface area. Again, this is optional, but I'm going to round this surface area to keep things simple. So the QuadGK function has calculated that the surface area of this three-dimensional shell is roughly 36.18 square units. As a sanity check, the surface area of a hollow open cylinder with a radius of 1.5 and a height of 4 is roughly 37.7 square units. So that makes sense that our surface area is slightly less than the surface area of this cylinder. To visualize this, we can reuse our 3D plots. Let's add some markdown text to display the surface area. In this visualization, you need to imagine that this shape is just a shell with an open end. As before, you can change the lower limit and the upper limit by using the sliders. As you can see, the plot updates automatically, as does the surface area calculation in the markdown cell. Fascinating, right? Now, we went through a lot of code for these 4 examples, so let's break here and recap what we just learned. Just by using this one function from the QuadGK.jl package, we were able to calculate the area under a curve, a volume of a solid of revolution, the arc length of a curve, and the surface area of a surface of revolution. In addition, we were able to generate models in both 2 dimensions and 3 dimensions to help visualize the integration concepts in a fun and interactive way. Thanks to numerical integration and the QuadGK.jl package, integration doesn't need to be some arduous, time-consuming process. Instead, integration can be simple and engaging, leaving you with more time for your discovery work. If you found this package to be useful and interesting, you can show your appreciation to everyone who worked on this package by going to their GitHub page and leaving them a star. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.